Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and negative 32 and 4 to the 6th power. In this Mometrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers, although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator. The number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. So that's our look at numbers and their classifications. From whole numbers to irrational numbers, we need to know what to call numbers so we can know what they mean.
Hey guys! Today we're going to take a look at the mathematical operations addition, subtraction, multiplication, and division. These four operations serve as the fundamental building blocks for all math, so it is crucial to have a solid understanding to build upon. Let's dive in. We use addition and subtraction to solve many real-world situations. Addition and subtraction are simply the mathematical terms used to describe combining and taking away. When we add, we are combining or increasing. When we subtract, we are taking away or decreasing. As a reminder, the symbol we use for addition is a plus sign. The answer to an addition problem is called the sum. The symbol we use for subtraction is a minus sign. And the answer to a subtraction problem is called the difference. Essentially, addition and subtraction are opposite operations. One adds value and the other deducts value. One strategy for visualizing these two operations is to use a number line. We will use a number line to illustrate the following examples. Let's imagine a situation that involves the sale of popcorn. For this scenario, let's assume that you are trying to raise money by selling bags of popcorn and you start with 20 bags. When your first customer arrives, they wish to purchase 4 bags of popcorn. This means that your remaining number of bags will decrease. We can represent this situation with a simple equation that involves subtraction. We started with 20 bags and we decreased by 4 or subtracted 4. Our subtraction equation is written as 20 minus 4 equals 16. On a number line, we can represent this deduction by starting at 20 and then moving backwards 4 units in the negative direction. Each jump backwards represents subtraction by 1. Now let's say you started with 20 bags of popcorn and ended up with 6 bags left at the end of the day. You need to replenish your stock in order to keep up your sales, so you make 4 more bags of popcorn. How many bags of popcorn do you now have available to sell? For this scenario, since we are looking at an increase of bags, we will use addition. This situation can be described using the equation 6 plus 4 equals 10. You had 6 bags initially and then combined that amount with 4 more bags. Now you have 10 bags in all. On a number line, addition is represented by jumps to the right in the positive direction. Each jump to the right represents the addition of 1 unit. So in this example, we would be starting at 6 and jumping 4 units to the right. We can see that we land on 10. It is important to notice that when using addition, the order of the values does not matter. For example, 10 plus 30 is the same as 30 plus 10. The placement or arrangement of the values has no effect on the outcome. Both arrangements would equal 40. However, the same is not true for subtraction. Does 30 take away 10 mean the same thing as 10 take away 30? Clearly not. We can see that the order matters when dealing with a situation involving subtraction. The technical term for this quality is known as the commutative property. Essentially, the property is true for operations where the values can move around, commute, and the outcome of the expression or equation will not change. The commutative property applies to addition, but not to subtraction. Another operation that also shares the commutative property is multiplication. Let's discuss multiplication together with division, as we did for addition and subtraction. Multiplication and division are similar to addition and subtraction in that they perform opposite functions. The function of multiplication is to represent multiple groups of a certain value, whereas division is designed to show the separating or subdividing of a value into smaller groups. As a reminder, the symbol we use for multiplication is a times sign. The answer to a multiplication problem is called the product. The symbol we use for division is a division sign, and the answer to a division problem is called the quotient. Multiplication is essentially a convenient and time-efficient way to show what's called repeated addition. For example, if you need to fill 30 bags of popcorn and each bag requires 60 kernels, it could take hours to count up how many kernels you need in total by just using addition. A faster and more efficient way to make this calculation would be to use repeated addition. Instead of counting each seed independently, we would group them up and add the groups together. The calculation would then become 30 groups of 60. This grouping, for the purpose of repeated addition, is the multiplication process at its core. 30 groups of 60 is written as 30 times 60, which is 1,800. So 1,800 kernels are required to fill up 30 bags of popcorn. Both addition and multiplication are commutative, because the order does not affect the answer. 30 groups of 60 gets us the same result as 60 groups of 30. Our last operation, division, can be considered multiplication's opposite. When we use division, we are essentially splitting up a large group into smaller subgroups. For our popcorn example, we can use division to answer the following question. How many bags of popcorn can I make using 1,800 kernels if each bag requires 60 seeds? This situation requires us to divide the large value, 1,800, into groups of 60. Each smaller subgroup will now represent a bag of popcorn. 1,800 divided into groups of 60 is represented as 1,800 divided by 60. In this case, the answer is 30. So 30 bags of popcorn can be made with our 1,800 kernels. As you can see, division is not commutative because the order of the values plays a crucial role in determining the answer. 1,800 divided by 60 is not the same thing as 60 divided by 1,800.
Hey guys, welcome to this Symmetrics video on fractions. Fractions can be simple or complex. In this video, we'll cover different types of fractions and how to add fractions with different denominators. So, what is a fraction? A fraction is a part of a whole, which means a fraction can never be a whole number. Think of it like this. Our circle is divided into 8 equal pieces. Let's say 3 pieces were filled in. That means that 3/8 of our circle is filled in. The top number is called the numerator. And our bottom number is called the denominator. When saying fractions out loud, the denominator will usually be spoken as the ordinal version of the number. You would say 1/8 instead of 8, or 1/3 instead of 3. Let's take a look at a list of our denominators and see how we would say them. As you can see, there are a couple of exceptions. If our denominator is 2, you could say half instead of second. Or if our denominator is 4, you can say quarter instead of fourth. But either one is acceptable. Hopefully that helps you to understand how fractions are defined and also how to actually say them out loud. But there are different types of fractions. Let's take a look at those. First, we have a proper fraction. A proper fraction always has a numerator, which we looked at, that is smaller than the denominator. Our example that we used before, 3/8. So our numerator, 3, is smaller than our denominator, 8. Some other examples of proper fractions include 4/5. An improper fraction is the opposite of a proper fraction in that the numerator is larger than the denominator. So while 3/8 is a proper fraction, 8/3 is an improper fraction because the numerator is larger than our denominator. Improper fractions are always equal to or greater than 1. That means that 9/9 is an improper fraction since it's equal to 1. There are also mixed fractions, which contain a whole number and a proper fraction. Here's an example. Note that the whole number 2 is followed by the proper fraction 3/4. We also have equivalent fractions. Equivalent fractions are 2 different fractions that name the same number. For example, 6/8 and 3/4 look different, but they're the same. 3/4 is just a simplified or reduced version of 6/8. To simplify 6/8, you just divide the numerator and the denominator by 2 to get 3/4. Now that we know the different types of fractions, we can explore how to add them. If two fractions have the same denominator, adding is a breeze. You just add the numerators together, and that gives you the answer. For example, so notice what we did to get 3/4. All we had to do was add from our first fraction the 1 from our numerator, and from our second fraction the 2 from our numerator. Add them together to get 3, and we just bring over our 4 from the denominator. Simple. But what happens if the denominators are different? Well, in that case, you have to convert the denominators to be the same. So let's take a look at an example. You can't really simplify 3/8 into anything that would easily add with 1/2, but we can do something with 1/2 that we could easily add with 3/8, and that's multiplying 2 by 4, which would give us 8. But whatever we do to our denominator, we also have to do to our numerator. So that would look like this. So our equation now becomes 3/8 plus 4/8 equals 7/8. Subtraction works the same way. If you're subtracting fractions with the same denominator, you can just subtract the top numbers, like in this example. So in this example, all we had to do was subtract our top numerators here, which gave us 2/4, which simplifies to 1/2. Simplifying numbers just makes them easier to work with. But if you're subtracting with a different denominator, you have to make the denominators match. For example, so in this example, 3/8 minus 1/4 is equal to x. We're kind of looking at a same issue like we did over here. We need our denominators to match. So we need to find out what can we do to make our denominators match. Well, in this case, we can multiply 4 times 2. But remember, we have to do the same thing that we do to the denominator, we must do to our numerator. So we can multiply it times 2, and then here's what we get. So once we multiply our second fraction here by 2, we get 3/8 minus 2/8, which gives us 1/8. So these problems were pretty easy because they had either the same denominator or were just really easy to convert. But let's look at one more equation that's a little trickier. So at first glance, it doesn't look like these numbers have much in common, such that we would be able to multiply or divide 4 by anything to get 7, or 7 by anything to get 4. So a lot of the times when you have problems like this, what you end up having to do is multiplying this fraction by the denominator of the other fraction. And likewise, we would multiply this fraction by the denominator of this fraction. So here's what that looks like. So after our multiplication, we end up getting a common denominator, which is 28. So now all we have to do is add our numerators together, which that gives us 45 over 28. And that's our answer. With this calculation, we found the least common denominator. The least common denominator is the smallest common number between denominators. Anytime you perform a calculation with different denominators, you must find the least common denominator to solve the problem.
Hello, and welcome to this video about the number line. In this video, we will explore how to read number lines, draw and plot points on a number line, and add and subtract with a number line. Let's get started. We will use a number line to represent numbers in counting order. The number to the left is always smaller than the number to its right. To draw a number line, we first start by drawing a straight line, and then we put arrows at the ends. The arrows represent the fact that the number line goes on forever in both directions. When dividing the number line with tick marks, it is important to place the tick marks equally spaced apart. This shows that the distance from any two numbers is the same. For example, the distance from 1 to 2 is the same as the distance from 2 to 3. The most important number on a number line is 0, because every other number is based off of how far away it is from 0. Numbers to the left of 0 are negative, and numbers to the right of 0 are positive. Number lines continue infinitely in either direction, so the number line you see is always only part of the whole number line. Because of this, even though 0 is the most important number, it might not show up on your number line. For example, your number line might look like this if you're trying to plot the grade you got on your test. Number lines can be used to represent a specific number. In the example we just mentioned, we can use the number line to represent a test grade of 94 by putting a dot above the number like this. Plotting a negative number would happen the same way. Simply put a dot over the number you are wanting to represent. The number line here shows the number -5. We can also use a number line to help us add and subtract numbers. Movement to the right is for addition, and movement to the left is for subtraction. To use the number line for adding and subtracting, we start by plotting a point at our first number. Then we move right or left, depending on the operation, the number of spaces matching the second number. Let's practice by adding -7 plus 5. We will start at -7, and since the operation is addition, we will move to the right 5 spaces. As you can see, we land on -2. Therefore, -7 plus 5 equals -2. Now let's try subtracting 9 minus 4. We will start at the number 9 on the number line, and since the operation is subtraction, this time we're going to move to the left. We move left 4 spaces, which lands us on 5. Therefore, 9 minus 4 equals 5.
Hey guys! Today we're going to take a look at conditional probability. This type of probability is all about finding the odds of something happening given that something else has already occurred. Let's start with a refresher on basic probability. The probability of something happening can be expressed as the number of desired outcomes divided by the number of total possible outcomes. Like this. Here's an example of a basic probability problem. There are 10 marbles in a bag. 3 are blue, 3 are red, and 4 are white. What are the odds of pulling out a red marble? To solve this, we'd place the number of desired outcomes on the top. In this case, it'd be 3 because there are 3 red marbles. And the total number of possible outcomes on the bottom. This is 10, since there are 10 total marbles in the bag. Seems pretty straightforward, right? Well, conditional probability adds a bit of a twist to this, as the objects or people in question often have more than one possible attribute. Let's look at another example problem. Out of 100 houses sold, 40 were sold with a garage only, 30 were sold with a pool only, and 10 were sold with both a garage and a swimming pool, leaving 20 houses sold with neither. Given that a house was sold with a garage, what are the odds that it was also sold with a pool? It is not immediately obvious what to do with all that information, but if we draw it as a Venn diagram, we can make more sense of it. We can now see the overlap between the houses sold with garages and the houses sold with pools, all within the larger set of houses sold. It's easier to see now that of the 50 houses that were sold with a garage, 10 of them also had a swimming pool. So the odds are 10 over 50, which can also be expressed as the fraction 1/5 or 0.2 or 20%. Fortunately, there's a faster way to do this than drawing a diagram every time you encounter a conditional probability question. There's a handy formula we can use. We read this formula as the probability P of event B happening given that event A has happened is equal to the probability of events B and A happening over the probability that event A has happened. In these types of problems, both probabilities on the right side of the equation are usually given or can be determined from a sentence or table. So in our sample problem, the P of B and A happening is the 10 houses out of 100 that were sold with both a garage and swimming pool. This fraction can be written as 1 over 10. The P of A is the probability of a house being sold with a garage, event A, which is 50 houses out of the 100, or 5 out of 10. Now that our formula is complete, we can simply divide 1 over 10 by 5 over 10, and we get 1 over 5, which is equal to 0.2 or 20%, just as we figured out from our drawing. Note that this formula can also be written as follows. The only difference is that the numerator is written as the intersection of event A and event B happening. In other words, the area where the two circles intersect in our drawing. Let's try one more with numbers that aren't quite so neat. In a small town, there are 216 men. 144 of them have brown hair, and 56 of them have mustaches. 24 of the men have brown hair and mustaches. What are the odds that a man chosen at random has a mustache, given that he has brown hair? Let's plug into our formula. The probability of event A, brown hair, and event B, mustache, is the 24 men with both divided by the 216 total men. The probability of event A, brown hair, is 144 divided by the original 216 men. We divide 24 over 216 by 144 over 216 using fraction division. The 216s can cross out, so we're left with 24 over 144. We can then divide this to get a decimal of roughly 0.16666 repeating. Or, in percentage form, that would be roughly 16.67%.
Hi and welcome to this video about polygons. In this video, we will explore 4 things. 1. What polygons are. 2. The different parts of a polygon. 3. Ways to classify polygons. And 4. How to determine the number of diagonals in a polygon. The term polygon is derived from the Greek words polis, meaning many, and gonia, meaning angle. So polygons have many angles. First, let's explore how polygons are constructed. Consider the geometric point, represented by a dot. The point is zero-dimensional. It has no length, width, height, nothing. Now let's consider 2 connected points. This is called a line, or a line segment. A line segment is one-dimensional. It has length, but no width or height. When multiple line segments are connected end to end, polygons such as this can be formed. Polygons are two-dimensional. They have no thickness, like this. In order to be a polygon, the shape must be closed. In other words, every endpoint must be connected to another endpoint. This figure is comprised of connected segments, but the result is not a polygon. This shape is closed, but not made up of any connected segments, so it is also not a polygon. A polygon is defined as a two-dimensional closed shape composed of line segments. The sides of polygons are called edges, and the angles created where the edges intersect are called vertices. Polygons also have as many edges as vertices. Polygons are named by the number of edges they have. This polygon has 3 edges, 3 vertices, and is called a triangle. The triangle has the smallest number of edges and vertices of any polygon. It is impossible to create a two-sided polygon. Some common polygons are quadrilaterals, which have 4 sides, pentagons, which have 5 sides, hexagons, 6 sides, heptagons, 7 sides, octagons, 8 sides, nonagons, 9 sides, decagons, 10 sides, and dodecagons, which have 12 sides. Though polygons with any number of edges have names, the general n-gon is typically used for all other polygons, where n represents the number of sides. For instance, a 30-sided polygon is called a triacontagon, but it's often simply called a 30gon. Polygons can be regular or irregular. Regular polygons have congruent edges and congruent vertices. For example, this is a regular quadrilateral. The edges are the same length and the vertices have the same measure. This is an irregular quadrilateral. The vertices have the same measure, but the edges have different lengths. This is an irregular quadrilateral. The edges are the same length, but the vertices have different measures. This is an irregular quadrilateral. Neither the edges nor the vertices have the same measure. Polygons can also be convex or concave. When one or more vertices of a polygon measures more than 180 degrees, the result is a concave polygon. For example, this is a convex hexagon. All the vertices measure less than 180 degrees. This is a concave hexagon. One vertex measures more than 180 degrees. Now remember, only polygons with 4 or more sides can be concave because it's not possible for a triangle to contain an angle measuring more than 180 degrees, which is a straight line. Concave polygons cannot be regular because all the vertices will never be the same measure. Polygons also contain diagonals. Diagonals are line segments joining two vertices that are not next to each other. As you can see here, this irregular convex pentagon has 5 diagonals. This is an irregular concave pentagon. It also has 5 diagonals, even though the concavity causes diagonals to lie outside the polygon. Triangles do not have diagonals because there is no way to connect two vertices with segments that are not edges. Now that you know the basics of polygons, let's use the diagrams to figure out a formula for finding the number of diagonals in any polygon. In this case, the number of diagonals connecting to each vertex is 2, which is 3 less than the number of vertices, 5. 2 diagonals connect to each vertex. This is true of all diagonals of all polygons. A nonagon has 9 minus 3 equal to 6 diagonals connecting to each vertex. The number 3 is not arbitrary here. From any vertex, diagonals cannot connect to the vertex itself or to the vertices that they are 1 away from, because it would be edges. That makes 3 vertices from every vertex that aren't included. To generalize this, we'll use n minus 3, where n is the number of vertices of the polygon. Now each vertex has the same number of diagonals connecting to it, so in this case we can see that the total number of diagonal connections to vertices is 5 times 5 minus 3, which is equal to 10. In general, we can say the total number of diagonal connections is n times n minus 3. When we figure out this total, though, we are counting each diagonal twice because diagonals have 2 endpoints. In order to figure out the number of unique diagonals, we need to divide our total by 2. In our pentagon, this looks like 5, which corresponds to our diagram. Therefore, for any size polygon, our equation can be written as this: n times parentheses n minus 3 all over 2, or divided by 2. Conceptually, this can be remembered as Using our formula, we can determine the number of unique diagonals in, for example, a 17gon, which is equal to 119 unique diagonals. We can also see algebraically that triangles have no diagonals. We can also figure out how many edges or vertices a polygon has by the number of unique diagonals. Suppose a polygon has 44 unique diagonals. how many edges does the polygon have? Alright, so here we are at an answer. N, the number of edges the polygon has, is either equal to 11 or -8. Because what we want to do is we want to make sure that we end with the result of 0, which means that n somewhere has to be 11 or -8 in order to get us multiplying 0 by another answer, resulting in 0. Since n can't be negative, because we can't have negative edges, it can't be -8. So we know that our answer is 11. The number of edges is 11, making it an 11gon.
Hi, and welcome to this video on the perimeter and area of a triangle. To get started, let's quickly review what perimeter and area measure. Imagine we have a triangular shaped yard. If we wanted to build a fence around our yard, we'd need to know the distance around the yard. This is the perimeter. If we wanted to buy sod for our yard so that we could have a lovely green space, we'd need to know the area of the yard so that we could buy the correct amount. And while it might be a bit unusual to have a yard that is the shape of a triangle, you might have part of a yard that you want to fence or sod shaped like a triangle. Okay, now that we know what perimeter and area are, let's figure out how to find the perimeter. We don't need any fancy formula or anything. All we need to do is add the length of the sides together. So if we know all the sides of our yard, we can easily find the perimeter. "20 meters plus 20 meters plus 12 meters gives you 52 meters of fence." Not much to that one. Notice that the answer is given in meters. That's because perimeter is a distance. Walking around the yard would mean walking 52 meters. That's all there is to it. No matter what type of triangle you have, just add up the length of the sides and you have your perimeter. Now let's deal with area. There is an actual formula for finding the area of a triangle. The formula is area equals 1/2 base times height. Let's quickly explain where that 1/2 comes from. The formula for the area of a parallelogram is area equals base times height. If we compare the two shapes, we can see that a parallelogram can be made by two equal-sized triangles. So we can say that a triangle is half a parallelogram, which is where the 1/2 comes from in the formula. For triangles, the formula for area does work a bit differently depending on the type of triangle. Let's start with right triangles. We have our formula, but the question we need to answer is which side is B and which side is H. For a right triangle like this one, B and H are the two sides adjacent or next to the right angle. It doesn't matter which is which, so let's say that B equals 6 centimeters and H equals 8 centimeters. Now we can plug them into our formula. It's always a good idea to substitute with parentheses to help keep things organized. We've even left the units in so that we can see what will happen with them. At this point, we only have multiplication left to do. So according to the commutative property of multiplication, we can rearrange before multiplying. Now let's solve this. Area equals 1/2 times 6, which is 3. 3 times 8 gives you 24. And centimeters times centimeters gives you centimeters squared. So we end up with our area as 24 centimeters squared. For area problems, the answer will always be in square units. That's because we're trying to determine how many square centimeters will fit in our triangle. We can see that clearly by looking at an isosceles right triangle that has legs measuring 5 units on some graph paper. How many squares will be inside the triangle? We can count them. First, we'll count the whole squares that fit inside, then we'll add the half squares. There are 10 full squares plus 5 half squares, for a total of 12.5 squares. If we use our formula, we'll find the same thing. Now we've seen the formula work and gained a better understanding of why the units are squared. All we have left to do is find the area of acute and obtuse triangles. Let's start with an acute triangle. Note that the height is always perpendicular to the base. From here, we can find the area. Here we have our area equals 1/2 times the base, which in this case is 12 centimeters, times the height, which is 8 centimeters. So we get 1/2 times 96 from 12 times 8, which gives us 48 centimeters squared. The same thing applies to obtuse triangles, except the height or altitude will often appear outside of the triangle, like this. We can see that the height of the triangle is 6 centimeters, and the side it is perpendicular to is the base, which measures 9 centimeters. We don't need the other two numbers at all, so let's plug in the base and the height. That's all there is to it. Here's one more for you to solve on your own. Try pausing this video and then finding the perimeter and area of this triangle. Think you got it? The perimeter is 34 meters and the area is 49 meters squared. Hi, and welcome to this video on tangent lines. Today we're going to explore what can happen when a circle and a line meet, and we'll start by exploring how these two shapes can interact. The most a line can intersect with a circle is by crossing over it like this. We can see that the line intersects the outside of the circle at 2 points and creates a line segment between those 2 points that is called a chord. A line that cuts across a circle in this way is called a secant to the circle. Another scenario would be a line that doesn't intersect the circle at all, like this. Even though the arrows on the line represent the line going on forever, it will never intersect with the circle. There really isn't much to say about this one, but we should be aware that it can happen. There's one other thing that can happen with a circle and a line, and it looks like this. In this case, the line only touches the circle at one point. This line can be described as a tangent to the circle or tangential. The point where the line and the circle touch is called the point of tangency. Looking closely at our diagram, we can see a radius of the circle meeting our tangential line at a 90-degree angle. For our line to be truly tangent, this must be true. If our line isn't exactly perpendicular to the radius at the point of tangency, it will actually touch the circle twice, though possibly very close together. We can see that with a close-up that shows the angles just a few degrees away from 90 degrees. Even if the angle were even closer to 90 degrees, such as 90.1 degrees and 89.9 degrees, this would still happen, though it would be harder to show in a diagram, at least without a microscope. Now, what if we're given a circle with a tangent line and we want to know the slope of the line? If we know the center of the circle and point of tangency, then we can figure it out. Let's take a look. We can see that the center of the circle is at the origin, or the point 0, 0, and the point of tangency is at -3, -5. Since we have 2 points on the radius, we can determine the slope of the radius using the slope formula. Let's call the center of the circle point 1 and the tangency point number 2. Remember, it doesn't matter which point we call 1 or 2, just that we need to be consistent on how we substitute once we decide. So this is going to be our x1, y1, and our x2, y2. M equals y2 minus y1 over x2 minus x1. Which gives us -5 over -3, which is equal to 5 over 3. So we found the slope of the radius, but that's not the final answer because we're trying to find the slope of the tangent line. Since the tangent line is perpendicular to the radius, we can find it by taking the negative reciprocal of the slope of the radius. Finding the negative reciprocal just means that we flip it over and change the sign. So the slope of the tangent line is -3 over 5.
Hello, and welcome to this video about line graphs. Today we'll explore what a line graph is and what type of data it's used to represent. We'll also learn how to use line graphs to interpret situations in the real world. Before we get started, let's review a few things. First, a graph is a diagram that shows the relationship between two quantities, which we call variables. These variables are measured along the x-axis and y-axis on a coordinate plane. A line graph is a type of graph that displays quantitative data as a series of points called markers, or data points. These data points are connected by straight line segments. The connected data points show the relationship between two variables. A line graph is typically used to show information that changes over time. Let's take a look at an example. This line graph shows the change in a company's profits over several years. The x-axis is labeled year and the y-axis is labeled profits. We see that line segments connect the data points plotted on the graph. Since the line segments are generally moving in a positive direction, we can say that the company's profits tended to increase from 2006 to 2013. Let's take a look at the line segment connecting the data points for the years 2009 and 2010. We can see that this particular line segment is positioned in a downward or negative direction. This tells us that the company's profits decreased from 2009 to 2010. What do you notice about the line segment connecting the data points for 2012 and 2013? They form a straight horizontal line. This shows that the company's profits neither increased nor decreased during this time frame. Instead, they stayed the same. When constructing a line graph on a coordinate plane, the x-axis is always used to plot the independent variable, and the y-axis is always used to plot the dependent variable. With line graphs, the independent variable is usually time. In the graph we just looked at, the independent variable is years, which is a measurement of time. The dependent variable is the factor that changes over time. In our example, the dependent variable is the company's profits, which increased and decreased from 2006 to 2013. Line graphs are an important part of our everyday lives because they can swiftly communicate data and trends. They're used in a wide variety of fields, including sales and marketing, science, psychology, economics, and business. Additionally, line graphs can be used to make predictions. Let's look once more at our line graph showing the company's change in profits. Based on the general trend shown, do you think the profits will increase or decrease in the future? We can infer that the profits may continue to increase based on the positive trend shown in previous years. Let's look at another line graph together. This graph shows how much time Dave spent playing video games each day. The horizontal x-axis shows the independent variable, which is days, and the vertical y-axis shows the dependent variable, which is minutes spent playing games. Each marker shows the data point for how many minutes of video games Dave plays each day. Let's use this information to answer some questions. Which day did Dave spend the most time playing video games? Dave spent the most time playing video games on day 4. We know this because the marker for day 4 is higher than the markers for the rest of the days shown. On day 4, Dave played games for 100 minutes. That's a lot of gaming. What is the difference in the amount of time Dave spent playing video games on day 2 and day 6? Looking at the markers, the graph shows that Dave played games for 70 minutes on day 2 and 90 minutes on day 6. The difference is calculated by subtracting. Since 90 minus 70 equals 20, the difference is 20 minutes. Dave spent 20 more minutes playing video games on day 6. How many minutes did Dave play video games altogether? To find the total amount of time Dave played video games, add the amount of minutes played each day. 30 plus 70 plus 60 plus 100 plus 10 plus 90 equals 360. Therefore, Dave spent 360 minutes playing games from day 1 through day 6. A line graph can show multiple sets of data if the same two variables are related. Graphing multiple data sets on a line graph can be very informative because they can be compared and contrasted. When this happens, each data set is typically represented by a distinct color. The line graph contains a key that explains what data set each color stands for. Let's take a look at a line graph that shows two sets of data. This graph shows how much money was raised in a school fundraiser each month. The horizontal x-axis shows the independent variable, which is month, and the vertical y-axis shows the dependent variable, which is amount raised. Each marker shows the data point for how much money was raised in each month shown. The two data sets are graphed in two different colors, blue and green. By reading the key beneath the graph, we see that green represents money raised by 7th grade students, and blue represents money raised by 8th grade students. Let's use this information to answer some questions. Pause the video after each question is asked. Then look at the graph and see if you can answer it yourself. When you're ready, resume and check your work. Which grade raised more money in September? 8th grade students raised more money than 7th grade students in September. Remember that blue data points represent 8th grade students and green data points represent 7th grade students. Looking at the markers for September, we see that the blue marker is higher than the green marker, so 8th grade students raised more money in September. Which grade raised more money in the months of June and August combined? The 8th grade students, shown in blue, raised $60 in June and $60 in August. 60 plus 60 equals 120, so the 8th grade students raised $120 in June and August. The 7th grade students, shown in green, raised $20 in June and $100 in August. 20 plus 100 equals 120. So the 7th grade students raised $120 in June and August. As you can see, both grades raised the same amount of money in the months of June and August combined. In which month did 8th grade students raise the smallest amount of money? How much money was raised? We can find the answer by examining the blue markers representing the 8th grade data points in each month. The month that the marker is placed the lowest is in May, when they raised $40. I have one last graph for you to analyze. This one is a little more challenging, but I know you can handle it. As you can see, this line graph displays 3 sets of data. Consider the following questions. Which variable is independent? Which is dependent? Explain. In which month was the number of computers sold in shop C almost identical to the number sold in shop B? In which months did shop A sell more computers than shops B or C? Pause this video and analyze the line graph, and see if you can answer these questions yourself. When you're ready, resume the video and we'll go over the answers together. Now that you've tried these problems yourself, let's go over them together. Which variable is independent? Which is dependent? Explain. The independent variable is months, which is on the x-axis. The independent variable is always measured along the x-axis, and it usually pertains to time. In this case, time is measured in months. The dependent variable is number of computers sold, which is on the y-axis. The value of the dependent variable relies on the independent variable. In this case, the number of computers each store sold depends on the month. In which month was the number of computers sold in shop C almost identical to the number sold in shop B? March. When we look at the markers for that month, we see that the red marker for shop B and the green marker for shop C almost overlap entirely. This indicates that the number of computers sold by each shop was about the same. In which months did shop A sell more computers than shops B or C? February and March. To find out when shop A sold the most, look for when the blue markers are higher than the green or red markers. Shop A sold 40 computers in February and 50 computers in March. Line graphs are useful tools for showing how factors change over time. Hi, and welcome to this overview of functions. In this video, we will be examining the nature of mathematical relationships between variables. As we work through some examples, our goal is to determine whether or not the criteria are met to define a special relationship known as a function. Let's take some time to review the basics of math rules or relations. When we are working with an equation, the value of variable x helps determine the value of the variable y. Y equals 2x plus 3. The x value can be thought of as the input into the math rule that is determined by the equation, and the y values that result are the output. The technical terms for all x values and y values are domain and range respectively. So in this equation, the range y is going to be the same as twice the domain x plus 3. We can use a table to lay out some of the different outcomes of the equation. So we have our equations here, and the different values of that x could be listed here. For instance, if we find out that x is -2, our problem would look like -2 times 2, which is -4, plus 3, which equals -1. A set of ordered pairs can also be used to show a mathematical relationship. The 5 elements of the domain and range from the table are shown here. In words, each x value is shown as an ordered pair with its corresponding y value. These ordered pairs can be graphed on a coordinate plane to show the relationship visually. The relation y equals 2x plus 3 is graphed here. The domain values are found on the x-axis, and the graph takes the shape according to the range values on the y-axis. Another convenient visual representation of a relationship is called a mapping, which shows a direct correspondence between the domain and range elements. Here are two examples. In map A, each input value maps to one output value, but in map B, the domain value 2 maps to two output values, 20 and 40. This simple image plainly shows the criteria to determine whether the relation given is a function. By definition, a relation is defined as a function if each element of the domain maps to one and only one element of the range. Not all relations are functions, but functions are a subset of relations. We have covered several representations of relations in this video. The following image shows 4 representations that show a relation that does not qualify as a function. At this point, we will focus on the graph of this relation to introduce the vertical line test, which allows you to quickly determine the function status of any graph that you are given. In short, if you draw a vertical line through a graph and hit only one point, then the graph represents a function. In the example we just showed, if you draw a vertical line through the domain value of -2, the line will pass through the range values of 2 and -2. Therefore, the relation fails the vertical line test. Here are more examples of this convenient tool to determine a function from a graph. Think you got the hang of it? Let's go through a few problems together and see. Is this a function? -2, 2, -3, 3, and -4, 4. In this set of ordered pairs, the domain values are -2, -3, and -4, and the range values are 2, 3, and 4. Because each domain value is paired with only one range value, this relation is a function. What about this set? 3, 2, 3, 3, and 2, 4. In this set, the domain values are 3 and 2, and the range values are 2, 3, and 4. Because the domain value of 3 is paired with 2 and 3 in the range, this relation is not a function. Here's one more set to figure out. 1, 2, 2, 2, 3, 2, 4, 2, and 5, 2. What do you think? Is this a function or just a relation? The domain of this relation is 1, 2, 3, 4, and 5, and the range is 2. Because each element of the domain is paired with 2, it satisfies the definition of a function. It is allowable for each element of the domain to be paired with the same element of the range. Remember the vertical line test? Which one of these graphs passes that test if we were to draw a vertical line through it? The first graph here passes the test because the vertical line only passes through one point. In the second graph, the vertical line passes through 2 points, so it is not a function. Now that we've gone through several different representations of functions, you should be well on your way to knocking out more complex equations down the road. Hi, and welcome to this video about the algebra of polynomial and rational expressions. In this video, we will explore multiplying polynomials, factoring polynomials, dividing polynomials, rational expressions, and operations with rational expressions. Before we get heavily into polynomial algebra, let's recap a few important terms. A polynomial is a mathematical expression of one or more algebraic terms, each of which consists of a constant multiplied by one or more variables raised to a non-negative integral power, such as a plus bx plus cx squared. The key pieces to remember are, number 1, polynomials consist of one or more terms, of the general form ax raised to the nth power, that are added or subtracted. The sample in the definition has 3 terms. Number 2, the coefficients of the terms can be any type of number. And number 3, the powers of the terms can only be non-negative integers, including 0. Let's look at some quick examples. 2x squared minus 4x plus 5 is a polynomial expression, but 2x raised to the 2.5 power minus 4x plus 5 is not a polynomial expression. Why? Because of the decimal exponent. Remember, the exponents in a polynomial expression have to be integers. 0.4x plus 1 is a polynomial expression, but x raised to the negative third power plus 1 is not because of the negative exponent. Now that we've looked at some polynomial expressions, let's look at the different types. A monomial is a polynomial consisting of one term. For example, x and 2 are monomials. A binomial is a polynomial consisting of two terms. X plus 1 and x cubed plus 4 are both binomials. A trinomial is a polynomial consisting of three terms. 12x raised to the fourth power plus 3x cubed plus 1 is a trinomial. A degree is the highest exponent in a polynomial. 2 is a degree 0 polynomial. X plus 2 is a degree 1 polynomial. And x squared plus 3 is a degree 2 polynomial. Now let's move on to multiplying. One of the traditional methods taught for multiplying polynomials is FOIL. This method highlights the need for organization. Multiplying polynomials is an application of the distributive property. The key idea is that every term of each polynomial needs to be multiplied by every term of every other polynomial. One way to help visualize and organize polynomial multiplication is with an area model, which looks like this. Let's multiply 3x plus 4 by negative 2x minus 5. So 3x times negative 2x gives you negative 6x squared. And then 4 times negative 2x gives you negative 8x. Then here you get 3x times negative 5 equals negative 15x. And then here you have 4 times negative 5, which gives you negative 20. So the product is negative 6x squared minus 8x minus 15x minus 20, which then simplifies to negative 6x squared minus 23x minus 20. The area model demonstrates how to multiply every term of one polynomial by every term of the other, and it is expandable for polynomials of any size. Let's try another example. Our terms on the left are 7b to the fifth and negative 2b squared. And our terms on the top are 2a cubed, negative 4a squared, a, and negative 12. We need to simply multiply all the terms, then add the resulting terms together. None of these terms are like terms, so they can't be combined. So our answer is So this is our final answer. As we'll see throughout this video, working with polynomials is almost identical to working with simple numbers. When we think of factors, for example, we may think of numbers that are multiplied to create another number. For example, 2 and 3 are factors of 6. 20 and 5 are factors of 100. Often, we look for numbers' prime factorization. The prime factorization of 30 is 2 times 3 times 5. Because all the factors are prime numbers. Think of factoring as undoing the area model we just explored. Often, the terms of polynomials have common factors. Consider this polynomial. Each term has a common factor of 5a squared. So this can be rewritten as 5a squared times 4b plus 2a plus 3b cubed plus 1. This is the prime factorization of the polynomial. It cannot be factored any further. Sometimes factoring happens in groups. It appears as if this polynomial cannot be factored. Rearranging to group the a terms and the b terms, we have this. Pulling out the common factors, we have this. Now we can see the common factor of 2x plus 1. So we have this. 2x plus 1 times a plus b squared. We can always check our factoring work by multiplying the factors to be sure we end up with the original polynomial. Polynomial division is closely related to multiplication and factoring. Consider the number 6. Its prime factors are 2 and 3. 2 times 3 equals 6. So 6 divided by 2 is 3, and 6 divided by 3 is 2. This polynomial has prime factors of 3x plus 4 and negative 2x minus 5. Negative 6x squared minus 23x minus 20 divided by 3x plus 4 gives you negative 2x minus 5. And then if you do negative 6x squared minus 23x minus 20 divided by negative 2x minus 5, that gives you 3x plus 4. One polynomial can be divided by another as long as the degree of the dividend is greater than or equal to the degree of the divisor. Here's how it works. First, make sure the exponents of both polynomials are in descending order and put a 0 in for any missing in the sequence. For example, 2x squared plus 1 would be 2x squared plus 0x plus 1. Divide the first terms. Here, the question is, how many times does 3x go into negative 6x squared? Then, we're going to multiply 3x plus 4 by negative 2x. Then, we'll subtract the product. Then, we bring down the next term in the divisor, and we repeat. How many times does 3x go into negative 15x? Multiply, and then subtract. There's a remainder of 0, so negative 2x minus 5 and 3x plus 4 are factors of negative 6x squared minus 23x minus 20, as we already knew. Rational expressions are closely related to rational numbers. The word rational comes from the word ratio. Just as rational numbers are defined as having the form integer over integer, rational expressions are defined by the form polynomial over polynomial. Here are some examples of rational expressions. When common factors occur in the numerator and denominator of a rational function, they can be divided to make 1. This is often taught as canceling out, but it actually stems from the fact that, for example, 2 divided by 2 equals 1. We can remove the common factors from these rational expressions. Rational expressions behave like fractions. To add or subtract them, we need to get a common denominator. For example, since one expression has 3x as a denominator and the other has x squared, a common denominator of 3x times x squared can be created. Remember to multiply each numerator by the same factor so that we are essentially multiplying each expression by 1. Now multiply through and simplify. To multiply them, we multiply straight across. And to divide them, we multiply by the reciprocal. And there you have it. Thanks for watching and happy studying.